Imagine a sound, so faint, so ancient. It's the echo of creation itself. It's not a sound you can hear with your ears, but one you can detect with incredibly sensitive instruments. This isn't the roar of a supernova or the hum of a distant galaxy, but something far more profound. It is a whisper from the universe's very first moments, a cosmic message in a bottle traveling across 13.8 billion years. This is the cosmic microwave background, or CMB, and it's more than just background noise. Think of it as a photograph of the baby universe, a snapshot taken when the cosmos was only 380,000 years old. That's less than a blink of an eye in cosmic terms. The CMB is the afterglow of the Big Bang, the electromagnetic radiation left over from the universe's fiery birth. It's a faint microwave glow that permeates all of space, an ethereal canvas painted across the entire sky. It's invisible to the naked eye, but if our eyes could perceive microwaves, the entire sky would appear to glow with a soft, uniform light. This light isn't coming from any specific object like a star or a galaxy. Instead, it's the collective radiation from every point in the distant universe, a sea of photons that have been traveling since the universe became transparent. What secrets does this ancient light hold? Why are scientists so obsessed with studying it? The answer lies in the fact that the CMB is a time capsule. It's a direct window into the early universe, a period when everything we see around us today, stars, galaxies, planets, even ourselves, was just beginning to form. It contains vital clues about the universe's origin, its composition, and its ultimate fate. Scientists often refer to the CMB as the oldest light in the universe. It's a tangible piece of the past, a physical record of a time before stars existed. It is a relic from an era when the universe was an incredibly hot, dense plasma, a cosmic soup of particles interacting at unimaginable energies. These photons have journeyed across vast distances, almost the entire expanse of the cosmos, to reach us today. Their story is the story of the universe itself. We're about to embark on a quest to understand this ancient echo. We'll explore the conditions that created it, the accidental discovery that revealed its existence, and the groundbreaking experiments that have mapped it with ever-increasing precision. We will explore the subtle patterns and faint whispers within this seemingly uniform glow, patterns that reveal the seeds of galaxies and the fundamental laws of physics. This is a journey to the very edge of the observable universe, a journey to the dawn of time. So, we have this snapshot, this cosmic photograph of the universe at just 380,000 years old. But what about the moments before that? What was happening in the darkness before the light of the CMB was finally unleashed? Picture, if you will, a universe far removed from the serene, star-studded expanse we observe today. Instead of galaxies gracefully swirling in the void, imagine a cauldron of unimaginable heat and density, a pressure cooker where the very fabric of reality was stretched to its limits. This wasn't the elegant, transparent cosmos we know, but rather an impenetrable fog, a swirling maelstrom of elementary particles. This is the era of the primordial soup. In those first few 100,000 years after the Big Bang, the universe existed as a plasma. Not the kind you find in fluorescent lights, but a far more extreme state of matter. Think of it as an ocean of protons, neutrons, and electrons, all swimming in a sea of photons, light particles. But these photons couldn't travel far. They were constantly bumping into charged particles, ricocheting off electrons like ping-pong balls in a hurricane. It was a cosmic dance of epic proportions, a chaotic ballet where light was forever trapped. Photons, the very messengers that would eventually carry the CMB to our telescopes, were effectively grounded. They couldn't propagate freely, making the universe utterly opaque. Imagine trying to see through a dense fog bank, where visibility is practically zero. That's what the universe was like back then. Why couldn't these photons escape this primordial melee? The answer lies in the incredibly high temperatures of the early universe. The heat was so intense, hundreds of thousands of degrees, that atoms simply couldn't form. Every time a proton and an electron tried to get together to form a hydrogen atom, the intense radiation would immediately blast them apart. This constant cycle of ionization and recombination kept the universe in a state of perpetual disequilibrium. The charged particles acted like an impenetrable barrier, trapping photons and preventing light from escaping. It was a cosmic stalemate, a universe on hold. So, for hundreds of millennia, light remained imprisoned, unable to travel freely across the cosmos. The universe was a featureless, glowing fog, a sea of energy waiting for its moment to break free. It would take a specific set of conditions, a cosmic cooling period, to finally set the stage for the release of the CMB and the dawn of a transparent universe. What precisely was this tipping point? How did the universe transition from opaque plasma to transparent vista? And what role did temperature play in this incredible transformation? Stay tuned, because the story is just beginning. But how could anyone have known? How could scientists, decades before the technology even existed to detect it, have predicted the existence of this faint, all-pervading microwave glow? Was it a lucky guess? A shot in the dark? Not at all. It was a triumph of theoretical physics, a testament to the power of human intellect to unlock the secrets of the universe. The story begins not with an accidental discovery, but with a bold and audacious idea: the Big Bang. In the 1940s, a brilliant physicist named George Gamow, along with his students Ralph Alpher and Robert Herman, began wrestling with the implications of the Big Bang theory. If the universe had indeed started from an incredibly hot, dense state, what would the consequences be? Gamow, a Russian-born American physicist known for his playful personality and groundbreaking work in nuclear physics, had a hunch. He believed that the early universe was a giant nuclear reactor, forging the elements we see around us today. This idea, known as Big Bang nucleosynthesis, became the cornerstone of their calculations. Alpher, a young and ambitious graduate student, took on the daunting task of calculating the abundance of different elements that would have been produced in the early universe. He painstakingly worked through complex equations, trying to understand how protons and neutrons combine to form helium, deuterium, and other light elements. Hermann Gamow's colleague provided crucial insights and helped refine the theoretical framework. Their calculations revealed something remarkable. If the Big Bang theory was correct, the early universe would have been incredibly hot, dense, and bathed in radiation. As the universe expanded and cooled, this radiation would have stretched and redshifted, transforming from high-energy gamma rays into lower-energy microwaves. In essence, the Big Bang would have left behind a faint afterglow, a cosmic echo of its fiery birth. Alpher and Herman even went so far as to estimate the temperature of this relic radiation. Their initial calculations suggested a temperature of around 5 degrees Kelvin, just 5 degrees above absolute zero. This was an extraordinary prediction, considering that no one had ever detected such a faint and uniform background radiation. Now, imagine the challenge. These scientists were attempting to detect something that was, in essence, everywhere and nowhere at the same time. It wasn't a point source like a star, but a pervasive background glow, a subtle hum across the entire cosmos. It was like trying to hear a pin drop in the middle of a roaring concert, except the concert was the universe itself. Sadly, their groundbreaking work was initially met with skepticism and even ridicule. The idea of a relic radiation from the Big Bang seemed far-fetched to many scientists at the time. Furthermore, the technology needed to detect such a faint signal simply didn't exist. The prediction, though brilliant, remained largely unnoticed, a whisper lost in the vastness of scientific discourse. One might wonder, why didn't Gamow and his team build the experiment themselves? The answer lies in the nature of scientific research at the time. Gamow was primarily a theorist, focused on developing and refining the theoretical framework. Building and operating experimental equipment required a different set of skills and resources, something that was beyond the scope of their research program. But their work, though initially overlooked, was far from in vain. Their theoretical predictions laid the groundwork for future searches, providing a crucial target for experimentalists to aim for. They had essentially given the scientific community a roadmap, a set of calculations that predicted what the CMB should look like and how warm it should be. They had given the scientists something to search for. Think of it like this. They weren't able to take the picture, but they precisely described what it would look like, its colors and brightness. This theoretical prediction, born from painstaking calculations and a deep understanding of nuclear physics, would ultimately guide the discovery of one of the most important pieces of evidence supporting the Big Bang theory. Their intellectual leap transformed cosmology from a field of speculation into a science of precise measurement. And somewhere, out there in the cosmos, the whispers of the Big Bang were still traveling. So, these brilliant minds, Gamow, Alpher, and Hermann, had predicted the existence of this faint, pervasive radiation. They had essentially sketched out the cosmic map. But where was the expedition to find it? Where were the intrepid explorers who would confirm their audacious theory? As fate would have it, the discovery of the cosmic microwave background wouldn't come from dedicated cosmological research, but from a rather unexpected source. A pair of radio astronomers trying to eliminate static. Picture this, it's 1964. Arnaud Penzias and Robert Wilson, two young scientists working at Bell Telephone Laboratories in Holmdel, New Jersey, are grappling with a frustrating problem. They're tasked with commissioning a massive horn-shaped antenna, a behemoth of metal designed to detect radio waves bounced off Echo and Telstar communication satellites. This was cutting-edge technology at the time, a testament to humanity's growing ambition to reach for the stars, or at least to bounce phone calls off them. But there was a snag. A persistent, annoying background noise was plaguing their measurements. No matter where they pointed the antenna, this faint, steady hiss remained. It was like trying to have a conversation in a room filled with static electricity. Now, Penzias and Wilson weren't cosmologists, they were radio engineers focused on practical applications, but this mysterious noise was interfering with their work, and they were determined to eliminate it. Their initial suspects? Local interference, urban noise, maybe even some malfunctioning equipment. They meticulously checked every connection, calibrated every instrument, and scrutinized every circuit. They even considered the possibility of military radar signals bouncing around. Nothing seemed to explain the persistent hiss. It was a cosmic riddle wrapped in an engineering problem. And then came the pigeons. Yes, you heard that right. Penzias and Wilson discovered that a pair of pigeons had taken up residence inside the antenna, leaving behind a rather substantial amount of, shall we say, organic material. Now, these weren't just any pigeons. They were, according to Wilson, large, white, die-hard pigeons who refused to be evicted easily. After thoroughly cleaning the antenna and humanely evicting the stubborn birds, Penzias and Wilson thought they had solved their problem. But alas, the mysterious noise persisted. This left them baffled. Could it be a flaw in the antenna itself? They considered this. They went over every inch of the antenna carefully to try and find something. Could it be a malfunction? The sound they were hearing was the sound of the universe. It was that faint static from the very early universe. Frustrated and increasingly puzzled, Penzias and Wilson reached out to other scientists for help. Little did they know their quest to eliminate static would soon lead them to one of the greatest discoveries in 20th century science. A chance conversation with colleagues at nearby Princeton University, researchers who were actively searching for the CMB, revealed that the mysterious noise perfectly matched the predicted characteristics of the relic radiation from the Big Bang. It was a eureka moment, a collision of serendipity and scientific inquiry. Penzias and Wilson had stumbled upon something far grander than a malfunctioning antenna or pigeon droppings. They had inadvertently detected the faint whisper of the early universe, the afterglow of creation itself. the implications were profound. This accidental discovery provided the first direct observational evidence supporting the Big Bang theory. It confirmed that the universe had indeed started from a hot, dense state, and that this early epoch had left behind a detectable relic radiation. Suddenly, the Big Bang theory wasn't just a theoretical construct. It was a physical reality, confirmed by experiment. The story of Penzias and Wilson is a reminder that scientific breakthroughs often come from unexpected places. It's a testament to the power of curiosity, persistence, and a willingness to follow where the data leads, even if it takes you down a rather pigeon-infested path. For their groundbreaking discovery, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978, forever cementing their place in the history of science. But the story of the cosmic microwave background was far from over. The initial discovery had confirmed its existence, but it revealed precious little about its properties. The universe had given us a tantalizing glimpse of its infancy, but the details remained blurry. What exactly did this faint, uniform glow tell us about the universe's origin, its composition, and its future? The quest to decipher the secrets of the CMB was just beginning. Penzias and Wilson's accidental discovery opened a window into the early universe, but it was a blurry window at best. The CMB appeared remarkably uniform, a seemingly featureless glow across the entire sky. But why was it so uniform? And more importantly, why was it a snapshot of the universe at just 380,000 years old? The answer lies in a pivotal moment in cosmic history, a time known as the last scattering surface, a moment when the universe underwent a dramatic transformation. Imagine the universe as a vast cosmic fog bank, illuminated from within. Before 380,000 years after the Big Bang, light, or photons, were constantly interacting with the hot, dense plasma that filled the cosmos. Protons, electrons, and photons were locked in a perpetual dance of absorption and re-emission. Photons couldn't travel far without bumping into a charged particle, making the universe opaque, like trying to see through a dense cloud. But as the universe expanded, it also cooled. This cooling was gradual, but inexorable, a cosmic countdown that would eventually trigger a profound change. As the temperature dropped to around 3,000 degrees Kelvin, a critical threshold was reached. Suddenly, protons and electrons could combine to form neutral hydrogen atoms. This was the moment of recombination, a deceptively simple name for an event that forever altered the course of cosmic history. Now, why is this moment so important? Because neutral atoms, unlike charged particles, don't interact strongly with photons. It's like the fog suddenly lifting, allowing light to stream freely. This marked the end of the era of constant scattering and the beginning of a transparent universe. The photons that were released at this moment, the photons that had been trapped in the cosmic plasma for hundreds of thousands of years, were finally free to travel across the vast expanse of space. These are the photons that make up the cosmic microwave background. They are the oldest light in the universe, the first light to travel freely after the Big Bang. And because they were released at a specific moment in time, when the universe was 380,000 years old, they provide us with a snapshot of the universe at that precise epoch. Think of it like taking a photograph of a crowd of people. If everyone is moving around randomly, the photograph will be a blur. But if everyone freezes in place for a split second, the photograph will capture a clear image of that particular moment. The last scattering surface is like that split second in the universe's history, the moment when everything froze and the photons were released, creating a clear snapshot of the early cosmos. So, the CMB isn't just any light. It's the light from the last scattering surface, the moment when the universe transitioned from opaque to transparent. It's a cosmic echo from a pivotal time, carrying invaluable information about the universe's composition, temperature, and density at that early stage. It's not just old light, It's information frozen in time. These photons, traveling billions of light years to reach us, are like cosmic messengers, whispering secrets of the early universe into our waiting telescopes. So what did these messengers have to say? What secrets did they carry across billions of light years? The first, and perhaps most astonishing, piece of information was the temperature. Initial measurements revealed that the cosmic microwave background was incredibly uniform, radiating at a temperature of just 2.7 degrees above absolute zero. That's minus 270.45 degrees Celsius, or minus 454.41 degrees Fahrenheit. Think about that for a moment. This is the temperature of the universe itself, a cosmic chill that permeates all of space. Now, 2.7 degrees Kelvin might not sound like much, but it's a crucial measurement. It perfectly matched the predictions made by Gamow, Alpher, and Hermann decades earlier, providing further confirmation that the Big Bang theory was on the right track. It was as if the universe itself was whispering, "Yes, you were right," across the vast expanse of time and space. This temperature rating was more than just a number. It was a validation of human intellect and a testament to the power of theoretical physics. But this near-perfect uniformity also presented a profound puzzle. How could regions of the universe that were so far apart, regions that had never been in causal contact with each other, have the same temperature? Imagine 2 cups of coffee sitting on opposite sides of a room. If you never mix them, they'll likely have different temperatures. But the CMB was telling us that the universe, at its infancy, was remarkably homogeneous, as if someone had stirred the entire cosmic coffee pot to perfection. This is known as the horizon problem, and it's one of the biggest challenges in cosmology. According to the standard Big Bang theory, regions of the universe that are separated by more than a certain distance, the so-called horizon distance, could not have exchanged information in the time since the Big Bang. They simply weren't close enough to have influenced each other. So, how could they have the same temperature? It's like finding identical snowflakes in 2 different snowstorms, an improbable coincidence that demands an explanation. The uniformity of the CMB is a cornerstone of the standard cosmological model, the framework that describes the evolution of the universe. It suggests that the early universe was in a state of thermal equilibrium, a state where energy was evenly distributed. But how did it get that way? What mechanism could have homogenized the temperature across the entire cosmos? Some have suggested that something must have occurred in the very early universe, something far more dramatic than the standard Big Bang theory describes. This uniformity challenges our understanding of causality, the principle that cause must precede effect. How could regions of space that were never connected have the same properties? This question has sparked countless debates and inspired some of the most innovative ideas in cosmology. One of the most prominent solutions is the theory of inflation, a period of exponential expansion in the very early universe. Inflation proposes that the universe expanded at an incredible rate, faster than the speed of light in the first fraction of a second after the Big Bang. This rapid expansion would have stretched the universe, smoothing out any initial irregularities and bringing distant regions into causal contact. Think of it like blowing up a balloon. If you start with a balloon that has some wrinkles and creases, as you inflate it, the wrinkles will smooth out and the surface will become more uniform. Inflation is like that, but on a cosmic scale. It would have stretched the fabric of space-time, smoothing out any temperature differences and creating the remarkably uniform CMB that we observe today. But the uniformity of the CMB, while providing crucial support for the Big Bang and the inflationary theory, was only half the story. If the early universe were perfectly smooth, then galaxies, stars, and planets wouldn't exist. After all, these structures formed from slight density fluctuations in the early universe, tiny variations in the cosmic soup that gravity amplified over billions of years. So if the CMB was perfectly uniform, where did these seeds of structure come from? Were there any hidden ripples in the early universe? The quest for these cosmic imperfections, these subtle variations in the CMB temperature, would soon become the driving force behind a new era of cosmological exploration, a quest that would push the limits of observational technology and challenge our deepest understanding of the universe. But within this incredibly uniform cosmic afterglow, there existed a subtle anomaly, a whisper hinting at a far grander cosmic dance. It wasn't an intrinsic feature of the CMB itself, not a seed of galaxies or a ripple from the early universe. Instead, it was a consequence of something far closer to home, our own motion through space. Imagine you're standing in the middle of a rainstorm. The raindrops appear to be falling straight down, right? But what if you start running? Suddenly the raindrops seem to be coming at you at an angle. This is because your motion is adding to the velocity of the raindrops, creating an apparent shift in their direction. This is the Doppler effect, and it plays a crucial role in understanding the cosmic microwave background. The Earth, our home planet, isn't sitting still in the universe. It's orbiting the Sun at a breakneck speed, approximately 67,000 miles per hour. The Sun itself is orbiting the center of the Milky Way galaxy, carrying all the planets with it. And the Milky Way galaxy is also moving, hurtling through space towards a mysterious region known as the Great Attractor. All of these motions combine to create a complex trajectory through the cosmos. As a result of this motion, we are essentially swimming through a sea of CMB photons. In the direction that we're moving, the CMB photons appear to be slightly blue-shifted, meaning their wavelengths are compressed, and their temperature appears slightly hotter. Conversely, in the opposite direction, the CMB photons appear to be slightly red-shifted, meaning their wavelengths are stretched and their temperature appears slightly cooler. This creates a distinctive pattern in the CMB map known as the cosmic dipole. On one side of the sky, the CMB appears ever so slightly warmer, about 3.35 Kelvin warmer than average. And on the opposite side of the sky, it appears ever so slightly cooler, about 3.35 millikelvin cooler than average. It's like the entire CMB is tilted, creating a hot pole and a cold pole. Now, 3.35 millikelvin might sound incredibly small, and it is. But it's the largest variation in the CMB temperature, significantly larger than the tiny fluctuations that seeded the formation of galaxies. The dipole is a signal that cosmologists must carefully account for before they can study the more subtle features of the CMB. Think of it like trying to see a faint star in the night sky. If there's a bright street lamp nearby, its glare will overwhelm the faint starlight, making it difficult to see. The cosmic dipole is like that street lamp, a bright signal that needs to be subtracted out before we can see the fainter details of the CMB. Understanding the cosmic dipole is crucial for several reasons. First, it confirms that we are not at rest with respect to the CMB. It tells us that the Earth, the Sun, and the Milky Way galaxy are all moving through space. Second, it allows us to determine our velocity relative to the CMB rest frame, the frame of reference in which the CMB appears perfectly uniform. This velocity is approximately 370 kilometers per second, or about 830,000 miles per hour. Subtracting out the dipole allows cosmologists to focus on the intrinsic variations in the CMB, the tiny temperature fluctuations that hold the key to understanding the universe's origin and evolution. It's like removing the background noise from a recording to hear the faint melody hidden beneath. These intrinsic variations, the long sought-after anisotropies, represent the seeds of all cosmic structures. They are the subtle imperfections in the early universe that gravity amplified over billions of years to form galaxies, clusters of galaxies, and ultimately, the large-scale structure of the cosmos. If the early universe were perfectly smooth, we wouldn't be here to observe it. So the next time you look up at the night sky, remember that you're not just standing still. You're hurtling through space at hundreds of kilometers per second, carried along by the Earth, the Sun, and the Milky Way galaxy. And as you move, you're subtly altering the appearance of the cosmic microwave background, creating a cosmic dipole that reveals our place in the grand scheme of the universe. But even after accounting for this grand motion, what subtle secrets still hide within the CMB's ancient light? So, we've painted this picture of a universe bathed in a near-perfect glow, a cosmic afterglow from the Big Bang. But consider this. What if the universe, at its birth, had been absolutely, flawlessly smooth? A blank canvas, devoid of any imperfections. It's a compelling thought experiment, but one with a rather stark conclusion. If that were the case, you, me, the Earth, the Sun, the Milky Way galaxy, all of it would not exist. Think of it like baking a cake. You can't just throw all the ingredients into a pan and expect a perfect cake to emerge. You need to have some variations in the mixture, some lumps and bumps that will eventually become the texture and structure of the cake. Similarly, the universe needed some initial imperfections, some seeds from which galaxies and clusters of galaxies could grow. These seeds, these subtle variations in density, are known as anisotropies. Imagine the early universe as a slightly uneven surface, with some regions being slightly denser than others. These denser regions would have exerted a stronger gravitational pull, attracting more matter and gradually growing into the cosmic structures we see today. It's a cosmic snowball effect, where tiny initial fluctuations are amplified over billions of years. But how do you find something so small, so subtle, hidden within this vast cosmic microwave background? It's like searching for a single grain of sand on an entire beach, a daunting task that requires incredibly sensitive instruments and ingenious techniques. These aren't just tiny ripples. They are the subtle blueprints of everything we see around us. Every star, every planet, every galaxy owes its existence to these slight deviations from perfection in the early universe. For cosmologists, the search for these minuscule ripples became a primary goal, an all-consuming quest to unlock the secrets of cosmic structure. It was a bit like searching for the Holy Grail. They knew it was there, but finding it was a different story. They theorized about them, searched for them, dreamed of them. The universe, after all, had written these ripples right into the fabric of space-time. The challenge was reading it. The difficulty in detecting the anisotropies was in their incredibly small size. We're talking about temperature fluctuations on the order of parts per 100,000. To put that into perspective, it's like trying to measure the height of a single blade of grass from a distance of 1,000 miles. This required a new generation of telescopes and detectors, instruments capable of peering into the depths of the cosmos with unprecedented precision. One might ask, were these density fluctuations random? Or were there underlying patterns? Did the fluctuations have a size or mass limit? These were questions that scientists were looking to answer. In the beginning, these questions were theoretical, and some scientists questioned if the anisotropies even existed. These weren't mere academic pursuits. Understanding the nature of these anisotropies would provide crucial insights into the fundamental laws of physics that governed the early universe. It would allow us to test theories of inflation, dark matter, and dark energy, and ultimately to understand how the universe evolved from a hot, dense plasma to the complex, structured cosmos we observe today. The journey to find these ripples would rewrite cosmic history. But to truly unlock the secrets hidden within those minuscule ripples, to finally see the face of the baby universe with clarity, required a bold new step. It demanded moving beyond ground-based observations, which are always limited by the Earth's atmosphere, the very air we breathe. It was time to take our telescopes to space. Enter COBE, the Cosmic Background Explorer, a satellite launched by NASA in 1989. Imagine, for a moment, the ambition behind this project. To design, build, and launch a spacecraft dedicated to mapping the faintest light in the universe. It was a monumental undertaking, a testament to human ingenuity and our insatiable desire to understand where we come from. This wasn't just another satellite, it was a time machine hurtling into the past. COBE was more than just a telescope. It was a flying laboratory, packed with sophisticated instruments designed to measure the cosmic microwave background with unprecedented precision. Its primary goals were twofold. First, to confirm that the CMB had a blackbody spectrum, meaning that it emitted radiation in a specific pattern predicted by the Big Bang theory. Second, and perhaps even more importantly, to search for those elusive anisotropies, those tiny temperature fluctuations that held the seeds of cosmic structure. Think of it like this. COBE was designed to answer two fundamental questions. Was the universe created in a Big Bang? And if so, how did galaxies form? These were questions that had puzzled scientists for decades, and COBE was poised to provide definitive answers. It was a high-stakes mission, a cosmic gamble with the potential to revolutionize our understanding of the universe. But why launch a satellite into space? Why not just build bigger and better telescopes on the ground? The answer lies in the Earth's atmosphere. Our atmosphere, while essential for life, is also a major obstacle to observing the CMB. It absorbs and distorts microwave radiation, blurring the image and making it difficult to detect the faint anisotropies. Imagine trying to take a picture of a distant mountain range through a thick fog. The fog scatters the light, blurring the details and making it hard to see the peaks. COBE, orbiting high above the atmosphere, was like removing the fog, allowing us to see the universe with crystal clarity. It was free from atmospheric interference, free from terrestrial radio noise, free to observe the CMB in all its glory. The satellite had three primary instruments, each designed to tackle a specific aspect of the CMB. There was the far-infrared absolute spectrophotometer, or FIRAS, which was designed to measure the spectrum of the CMB with incredible accuracy. There was the differential microwave radiometer, or DMR, which was designed to map the temperature of the CMB across the entire sky. And there was the diffuse infrared background experiment, or DIRB, which was designed to search for infrared radiation from the early universe. Together, these instruments created a powerful suite to observe the CMB. The DMR instrument was of particular importance to the search for anisotropies. It consisted of 6 differential radiometers, each designed to measure the temperature difference between 2 points on the sky. By comparing these temperature differences, the DMR could create a map of the CMB with unprecedented sensitivity. It was like having 6 incredibly sensitive thermometers, each capable of detecting temperature changes on the order of parts per 100,000. COBE represented a monumental leap in observational cosmology, a technological marvel that would forever change our understanding of the universe. Its mission was nothing less than to provide definitive answers about the early universe, to confirm the Big Bang theory, and to reveal the seeds of cosmic structure. It was a mission driven by curiosity, by the relentless pursuit of knowledge, and by the unwavering belief that the universe is knowable. But what would COBE discover? Would it find the elusive anisotropies? Would it confirm the Big Bang theory? The world waited with bated breath. Little did they know, cosmic history was about to be rewritten. But what would COBE discover? Would it pierce the cosmic veil and reveal the long-sought seeds of galaxies? Would it confirm once and for all the grand narrative of the Big Bang? The answer came in 1992, a year that would forever be etched in the annals of cosmology. The COBE team, led by George Smoot, announced their groundbreaking discovery, a moment that sent shockwaves through the scientific community and beyond. They had found them, the long-sought anisotropies, the primordial seeds from which cosmic structure grew. But these weren't colossal in-your-face deviations. These were subtle, incredibly faint temperature fluctuations in the cosmic microwave background, on the order of parts per 100,000. Imagine taking a photograph of the moon and discovering hidden within the shadows the faint outlines of mountain ranges. That was the magnitude of COBE's discovery. Think of these temperature fluctuations as tiny wrinkles in the fabric of space-time, ripples in the cosmic ocean that existed when the universe was only 380,000 years old. These weren't just random imperfections. They were the imprints of density variations, regions where matter was slightly more concentrated than average. These minute overdensities became the gravitational wellsprings for the formation of galaxies and clusters of galaxies. They represented the point where all of space began to come together in a magnificent creation. It was a moment of profound scientific validation, a triumph of human intellect and technological prowess. The Big Bang model, once a controversial theory, was now firmly cemented as the leading explanation for the origin and evolution of the universe. It was, if the universe itself had whispered its secrets to humanity, revealing the ancient blueprint of its cosmic architecture. George Smoot, with a mixture of scientific rigor and infectious enthusiasm, famously declared that these anisotropies were like seeing God. Now, that statement might raise a few eyebrows, but it captures the sheer awe and wonder that the COBE discovery inspired. It was a glimpse into the very beginning, a revelation of the processes that shaped the cosmos we inhabit today. But why did this discovery matter so much? Because without these tiny temperature fluctuations, the universe would be a vastly different place. There would be no galaxies, no stars, no planets, and certainly no life. The universe would be a uniform, featureless void, a cosmic wasteland devoid of complexity and beauty. These ripples are why we are here. The COBE discovery ushered in a new era of precision cosmology, a period where scientists could move beyond qualitative descriptions and begin to make precise quantitative measurements of the universe's properties. It opened the door to a deeper understanding of dark matter, dark energy, and the inflationary epoch, mysteries that continue to challenge and inspire cosmologists to this day. Now that these first seeds were discovered, the door to a deeper understanding was opened, and cosmology would never be the same. This discovery didn't just stay within the scientific community. The images of COBE's CMB map, with its mottled patterns of red and blue, became iconic representations of the Big Bang, appearing in newspapers, magazines, and documentaries around the world. It captured the public imagination, inspiring a sense of wonder and a renewed appreciation for the vastness and complexity of the cosmos. This picture allowed people to see, with their own eyes, the echoes of creation. Following COBE's triumph, cosmology was propelled into the new age. What would this new age of discovery hold, and what new mysteries would these new discoveries hold? Only time would tell. But even today, cosmologists are still studying that one photograph in the hopes of unlocking even more secrets to the universe's past. But the story doesn't end there. It's as if COBE, having shown us the first blurry snapshot, whispered, "There's more to see, much more detail to uncover." Could we sharpen the focus? Could we zoom in on those tiny temperature fluctuations and reveal the intricate patterns hidden within? The answer, it turned out, was a resounding yes. Imagine a cartographer charting an unexplored continent with a crude map, barely able to distinguish mountains from valleys. That was COBE's map of the CMB. Now, imagine that same cartographer armed with satellite imagery revealing every river, every forest, every village. That's the leap in resolution that was promised by the Wilkinson Microwave Anisotropy Probe, or WMAP. Launched in 2001, WMAP represented the next generation of CMB observation. It was NASA's ambitious attempt to map the CMB anisotropies with unprecedented accuracy and sensitivity. Named in honor of David Wilkinson, a pioneering cosmologist who dedicated his life to studying the CMB but tragically passed away before the mission's launch, WMAP was designed to build upon COBE's groundbreaking discoveries and provide a truly detailed blueprint of the early universe. Why was a sharper look so important? Because the patterns encoded in the CMB anisotropies hold the key to unlocking some of the universe's deepest secrets. The size, shape, and distribution of these temperature fluctuations reveal information about the universe's age, its composition, its geometry, and its evolution. It's like reading the DNA of the cosmos, deciphering the genetic code that governs its structure and destiny. WMAP was equipped with advanced radiometers, far more sensitive and precise than those on COBE. The probe operated from a stable orbit about 1.5 million kilometers from Earth at the second Sun-Earth Lagrange point. This location allowed for a stable thermal environment and continuous observations, away from the constant changes in weather on Earth and also shielded from the interference of Earth's radiation. The radiometers were capable of detecting temperature differences as small as a few millionths of a degree. This would allow WMAP to create maps with much higher resolution and sensitivity than COBE. The mission would be able to detect subtle changes in temperature, which would help with the ability to collect more data. But WMAP wasn't just about better technology. It also represented a paradigm shift in how cosmologists approached the study of the CMB. While COBE had focused on simply detecting the anisotropies, WMAP was designed to measure them with enough precision to determine key cosmological parameters with unprecedented accuracy. It was about transforming cosmology from a field of discovery into a field of precision measurement. The mission wanted to extract as much data as possible from the photograph of the baby universe. Picture this. WMAP was equipped with not just one, but several radiometers operating at different frequencies. This was crucial for distinguishing the true CMB signal from foreground contamination, such as emission from our own galaxy. It's like listening to a symphony with multiple microphones, each capturing a different instrument. By combining the information from all the microphones, you can isolate the individual sounds and understand the overall composition. This allowed scientists to remove sources of error and create a more accurate image of the CMB. The data that WMAP would obtain would give scientists an idea of the age of the universe, what makes up the universe, and how it is geometrically shaped. To say the science community was excited would be an understatement. What secrets would WMAP reveal? How would it refine our understanding of the universe's origin and evolution? Would it confirm the inflationary theory? Would it shed light on the nature of dark matter and dark energy? The answers were eagerly awaited, and the stage was set for another revolution in cosmology. The answers WMAP would obtain would change how scientists saw the universe. And as the data began to pour in, it became clear that WMAP was about to deliver on its promise, a detailed blueprint of the early universe, a treasure map to unlock the secrets of cosmic history. But even as WMAP soared into the cosmos, carrying with it the hopes and dreams of a generation of cosmologists, a crucial question lingered. What story would this new, incredibly detailed map tell? What secrets were waiting to be unlocked from the faintest whispers of the early universe? The answer, when it finally arrived, would reshape our understanding of everything. Imagine receiving a package you have been waiting for your entire life. You open it, and what do you see? Inside are not just pretty pictures, but a cosmic decoder ring, a key to unlock the secrets of the universe. That is exactly what WMAP delivered. The maps that WMAP produced were more than just pretty pictures. They were a treasure trove of data, a gold mine of cosmological information that allowed scientists to measure the universe's age, composition, and geometry with unprecedented precision. So, what did this cosmic decoder ring reveal? First and foremost, WMAP confirmed that the universe is roughly 13.8 billion years old. That is a number so vast it almost defies comprehension. To put it into perspective, if the entire history of the universe were compressed into a single year, human civilization would only appear in the last few seconds of December 31st. This discovery was pivotal in understanding the timeline of the cosmos. But WMAP didn't just tell us when the universe was born, it also revealed what it is made of. Here's where things get really interesting. WMAP's data showed that the universe is composed of roughly 5% ordinary matter. This is the stuff we're familiar with, the atoms that make up stars, planets, and everything we see around us. So, if we were to imagine the entire universe as an ocean, all the familiar matter would be the size of a teacup. Then there is dark matter, an invisible, mysterious substance that makes up about 27% of the universe. We can't see it, we can't touch it, but we know it's there because of its gravitational effects on visible matter. It acts like scaffolding holding galaxies together. It has been described by some as the ghost matter of the universe. And finally, there is dark energy, an even more enigmatic force that makes up about 68% of the universe. Dark energy is thought to be responsible for the accelerating expansion of the universe, pushing galaxies further and further apart. It is a sort of anti-gravity force that seems to be winning the cosmic tug of war. Some would even call it one of the biggest mysteries of modern science. These proportions weren't just numbers, they represented a profound shift in our understanding of the cosmos. Most of what makes up the universe is invisible and mysterious. It is as if we have only scratched the surface of cosmic understanding. WMAP's data provided strong support for the standard lambda CDM model of cosmology. This model combines the Big Bang theory with the concepts of cold dark matter and a cosmological constant represented by the Greek letter lambda, which accounts for dark energy. It is the current best explanation for the universe's origin, evolution, and large-scale structure. But even as WMAP painted a clearer picture of the universe, it also raised new questions and new challenges. But even as WMAP painted a clearer picture of the universe, it also raised new questions and new challenges. If those maps were so precise, so meticulously crafted, what were they actually telling us beyond the basic composition? What secrets were hidden within the intricate patterns of hot and cold spots? The answer, surprisingly, involves sound. Not the kind of sound you can hear with your ears, but sound nonetheless. A cosmic symphony echoing from the very early universe. Think of it like this. Imagine dropping a pebble into a still pond. It creates ripples, waves that propagate outward from the point of impact. Now imagine the early universe as a pond filled not with water, but with a hot, dense plasma of protons, electrons, and photons. And imagine that instead of a single pebble, there were countless imperfections, tiny density fluctuations scattered throughout this cosmic pond. These fluctuations, seeds of all structure, are like those pebbles. These fluctuations acted as sources of pressure, which in turn created sound waves, literally compression and rarefaction of the plasma. These sound waves propagated through the early universe like ripples spreading across a pond. These waves were not like the sound waves we know. They weren't traveling through air, but through the super-hot, super-dense plasma that made up the early universe. They are acoustic oscillations, and scientists can learn more about the state of the early universe by understanding them. But how do we hear these ancient sounds? The answer lies in the CMB itself. The hot and cold spots in the WMAP data are not random. They reveal a characteristic pattern of peaks and troughs, a distinct signature that scientists call acoustic peaks. Think of it like looking at a musical score. The peaks and troughs represent different notes, different frequencies of sound waves that were present in the early universe. When the universe finally cooled enough for atoms to form, roughly 380,000 years after the Big Bang, these sound waves were effectively frozen in place, imprinted on the cosmic microwave background like a snapshot of a cosmic concert. The size and spacing of these peaks provide a wealth of information about the universe's properties. It is like hearing the echoes of the universe's first sounds. Imagine you are a musician trying to understand the acoustics of a concert hall. You can learn a lot about the size and shape of the hall by listening to the echoes of your music. Similarly, cosmologists can learn a lot about the size, shape, and composition of the universe by studying the acoustic peaks in the CMB. Are we listening to a flute piano or a full orchestra? By analyzing the precise positions and amplitudes of these peaks, scientists can determine key cosmological parameters with incredible accuracy. They can measure the density of ordinary matter, the density of dark matter, and the overall geometry of the universe. It's like tuning a cosmic instrument, using the sound waves to fine-tune our understanding of the universe. But how do we actually measure these acoustic peaks? It's not like we can just listen to the CMB with a giant microphone. Instead, cosmologists use sophisticated statistical techniques to analyze the patterns of hot and cold spots in the WMAP data. They create a power spectrum, a mathematical representation of the distribution of temperature fluctuations across the sky. This power spectrum reveals the characteristic peaks and troughs, the telltale signs of the acoustic oscillations. Think of it like analyzing the sound waves produced by a musical instrument. By measuring the frequencies and amplitudes of the different harmonics, you can identify the instrument and understand its physical properties. Similarly, cosmologists can identify the properties of the early universe by analyzing the acoustic peaks in the CMB power spectrum. It is a symphony written in light and heat, a cosmic melody composed in the first moments of creation. And by listening carefully, by analyzing the subtle patterns in the CMB, we can begin to understand the music of the universe. The universe is full of sound. It just depends on how you listen to it. Perhaps you are now asking yourself, so we have this snapshot, we've heard the echoes, but what about the light itself? Can we learn more by looking at the light? Well, it turns out that there is more to light than just temperature, and understanding it would require delving into a world of polarization and the very fabric of space-time. But even as WMAP painted a clearer picture of the universe, it also raised new questions and new challenges. If those maps were so precise, so meticulously crafted, what were they actually telling us beyond the basic composition? What secrets were hidden within the intricate patterns of hot and cold spots? The answer, surprisingly, involves sound. Not the kind of sound you can hear with your ears, but sound nonetheless. A cosmic symphony echoing from the very early universe. Perhaps you are now asking yourself, so we have this snapshot. We've heard the echoes, but what about the light itself? Can we learn more by looking at the light? Just imagine if you had the opportunity to build the ultimate cosmic surveyor. What would it look like? What kind of technology would it need? In 2009, the European Space Agency, or ESA, launched a satellite that did just that. It was called Planck, and it represented the next generation of cosmic microwave background observation. It was the successor to COBE and WMAP, the culmination of decades of research and development. Planck was designed to push the boundaries of precision measurement and extract nearly all the cosmological information encoded in the CMB temperature anisotropies. The mission's name came from Max Planck, a German physicist and one of the founders of quantum theory. Planck was bigger, better, and bolder than anything that came before it. It was equipped with instruments far more sensitive than WMAP, capable of detecting even fainter temperature fluctuations in the CMB. It had higher resolution, allowing it to see finer details in the cosmic microwave background patterns. It even had broader frequency coverage, allowing it to distinguish the CMB signal from foreground contamination with even greater accuracy. How much more sensitive was Planck? Imagine trying to measure the thickness of a human hair from a distance of 10 kilometers. That's the level of precision we are talking about. Planck was a marvel of engineering, a testament to human ingenuity and our relentless pursuit of knowledge. But Planck was more than just a souped-up version of WMAP. It was designed with a specific goal in mind. The main mission was to refine our understanding of the universe, to test the standard cosmological model with extreme rigor. Could the model we have created hold up to the most stringent test possible? The satellite was designed to measure not just the temperature of the CMB, but also its polarization, the orientation of its light waves. This opened a new window into understanding cosmic history. The polarization of the CMB can reveal information about the distribution of matter in the early universe, about the presence of gravitational waves, and about the epoch of reionization, when the first stars and galaxies began to form. It was like adding color to a black and white photograph, bringing new features into focus. To achieve its ambitious goals, Planck was placed in a unique orbit. It orbited the Sun in sync with the Earth, but always remained on the opposite side of our planet. This allowed it to maintain a stable thermal environment and avoid interference from the Earth's magnetic field, a critical feature to ensure consistent and accurate observations. Think of it like a cosmic hide and seek. Planck was carefully positioned to hide from the sun and earth, allowing it to focus on the faint whispers from the early universe. Planck was not just about looking at the early universe, but also the future of the universe. By refining our understanding of dark energy and dark matter, the mission could shed light on the ultimate fate of the cosmos. The ESA poured more than 700 million euros into this ambitious mission, a testament to the commitment to understanding the universe. The science community knew that the data Planck would obtain could rewrite the cosmology textbooks. Planck's observations spanned more than 4 years, gathering data that would keep cosmologists busy for years to come. Imagine the anticipation, the excitement, and perhaps even a little bit of trepidation as the first data began to pour in. What would Planck reveal? Would it confirm our current understanding of the universe? Or would it challenge everything we thought we knew? What followed was a meticulous process of data analysis, a cosmic detective story where scientists sifted through mountains of information to find the faintest clues about the early universe, and what they discovered would once again change how we see the universe. But even with the incredible power of Planck, some mysteries remained. A few perplexing anomalies in the CMB data continued to defy explanation, hinting at the possibility of new physics, or perhaps even a breakdown of our current cosmological assumptions. Were these just statistical flukes, random noise in the data, or were they signs of something deeper, something fundamentally new about the universe? The debate continues to this day, fueling ongoing research and inspiring new ideas. So while Planck provided the most precise map of the early universe ever created, it also reminded us that there is still much we don't know. It's a humbling reminder that the universe is full of surprises and that our quest for knowledge is never truly complete. The story of Planck is a story of scientific triumph, but also a story of enduring mystery. What did those Planck results ultimately say about the universe? The answers may surprise you. So while Planck provided the most precise map of the early universe ever created, it also reminded us that there is still much we don't know. It's a humbling reminder that the universe is full of surprises, and that our quest for knowledge is never truly complete. The story of Planck is a story of scientific triumph, but also a story of enduring mystery. What did those Planck results ultimately say about the universe? The answers may surprise you. Did Planck rewrite the textbooks entirely? Did it throw the standard cosmological model into disarray? Not exactly. In fact, one of Planck's most significant achievements was confirming the picture of the universe that had been painstakingly assembled over decades of research, particularly by WMAP. It was as if the universe itself was saying, "Yes, you were on the right track all along." Planck's data provided the most accurate measurements of cosmological parameters to date. It refined our understanding of the universe's age, pegging it at approximately 13.82 billion years, with an uncertainty of only 37 million years. Imagine knowing the age of something that's been around for nearly 14 billion years down to the nearest few million. That's precision on a cosmic scale. It also refined our knowledge of the universe's composition, confirming the existence and proportions of dark matter and dark energy, those mysterious components that make up the vast majority of the cosmos. Planck's measurements slightly tweaked the percentages, but the overall picture remained the same. The universe is dominated by dark energy, followed by dark matter, with ordinary matter making up only a tiny fraction. But what made Planck so remarkable was its ability to test the standard cosmological model with extreme rigor. This model, known as lambda cold dark matter, is the framework that cosmologists use to describe the evolution of the universe from the Big Bang to the present day. It incorporates the ideas of inflation, dark matter, and dark energy, and it has been remarkably successful at explaining a wide range of observations. Planck's data provided strong support for this model, confirming many of its key predictions with unprecedented accuracy. The agreement between the model and the data was, in a word, remarkable. It was as if the universe was perfectly described by a set of equations that had been written down by human beings. This confirmation was a major triumph for cosmology. It meant that we were on the right track in our quest to understand the universe. It also gave us confidence that the standard cosmological model is a reliable framework for further research. The European Space Agency called this data release the culmination of the mission. Scientists from around the world celebrated the confirmation of the most accurate parameter to date. The results represent the current benchmark in cosmic microwave background cosmology. But one might ask, if Planck largely confirmed what we already knew, was it really worth all the effort and expense? Did it simply reinforce existing theories without providing any new insights? The answer is a resounding yes. Refining the model and confirming our picture of the cosmos allowed cosmologists to understand the universe with better detail, and also pointed to new questions for the future. The data helped improve our understanding of how the early universe evolved and the composition of all things. It showed that the initial conditions in the early universe were nearly perfect, which is essential for supporting current observations. Perhaps you're wondering what is next. What new horizons are on the edge of scientific vision? If we could only peer beyond temperature fluctuations, what other hidden truths would be revealed? So while Planck provided the most precise map of the early universe ever created, it also reminded us that there is still much we don't know. It's a humbling reminder that the universe is full of surprises, and that our quest for knowledge is never truly complete. The story of Planck is a story of scientific triumph, but also a story of enduring mystery. What did those Planck results ultimately say about the universe? The answers may surprise you. Perhaps you are wondering what is next. What new horizons are on the edge of scientific vision? If we could only peer beyond temperature fluctuations, what other hidden truths would be revealed? What if light, the very messenger that has carried information across billions of years, had more to say? What if it held secrets beyond what its temperature could tell us? The answer, it turns out, lies in a property of light that we often take for granted: polarization. Think of light as a wave, like a ripple moving across a pond. But unlike water waves, light waves can vibrate in any direction. Polarized light, on the other hand, is light whose waves are all vibrating in the same direction. It's as if you took that pond and somehow forced all the ripples to move only up and down or only side to side. Why should we care about the orientation of light waves? Because the polarization of the cosmic microwave background is not random. It carries within it a wealth of additional cosmological information, a hidden layer of data that can help us to understand the early universe in even greater detail. Imagine light as a cosmic messenger, carrying information from the distant past. But this messenger isn't just shouting out loud, it's also whispering secrets in code using the subtle language of polarization. If temperature is the volume of the message, polarization is the tone. This polarization arises from scattering processes in the early universe. Think back to the time when the universe was a hot, dense plasma, a soup of particles interacting at unimaginable energies. Photons, the particles of light, were constantly bouncing off electrons like ping-pong balls in a hurricane. These collisions imprinted a specific polarization pattern on the CMB photons, a pattern that reflects the conditions of the early universe. What kind of conditions, you might ask? Density fluctuations, for one. The polarization of the CMB is directly related to the density fluctuations that existed in the early universe, the same fluctuations that gave rise to galaxies and clusters of galaxies. By measuring the polarization patterns, we can get a more detailed picture of these fluctuations and understand how they evolved over time. It is like having a more precise map with finer details and clearer contours. Why is CMB polarization such a big deal? It provides an independent check on our cosmological models, allowing us to test our understanding of the universe in a new and powerful way. It is like having a second witness to a crime, someone who can corroborate the testimony of the first witness. It allows you to study the universe through a new set of data. The discovery of CMB polarization opened a new window into understanding cosmic history. It's like finding a hidden room in an ancient castle, a room filled with forgotten treasures and long-lost secrets. What treasures, you might ask? The CMB offers hints at an elusive epoch in the universe's history. So, we've shown a light, quite literally, on the temperature fluctuations within the cosmic microwave background. But what if the real story isn't just about how much light there is, but about how that light is oriented? Imagine looking at the universe through a polarizing filter, the kind you might use to cut glare on a sunny day. What you'd see is a hidden pattern, a subtle arrangement in the way the light waves are vibrating. This is polarization, and within the CMB, it's a game changer. CMB polarization comes in two distinct flavors, each revealing a different aspect of the early universe. E modes and B modes. Think of them like two different dances, each with its own unique steps and rhythm. E modes, the more readily detected of the two, exhibit gradient-like patterns, resembling the way iron filings align themselves around a magnet. These E modes are primarily generated by density fluctuations in the primordial plasma, the same fluctuations that gave rise to the temperature variations we've already explored. So, in a sense, E modes are a confirmation, a second opinion, on what we already know about the early universe. They provide a robust consistency check, reinforcing the standard cosmological model. But what about B modes? That's where things get really exciting. B modes are characterized by curl-like patterns, a swirling vortex of polarization that hints at something far more profound. These B modes are fainter, more elusive than their E mode counterparts, and their origins can be traced to two primary sources. The first, and perhaps less glamorous, is gravitational lensing. As CMB photons travel across billions of light years, their paths are bent and distorted by the gravity of intervening galaxies and dark matter structures. This gravitational lensing effect can transform E modes into B modes, blurring the lines and making it harder to isolate the truly primordial signal. It is like trying to hear a whisper in a crowded room. All that background noise can easily drown out what you are looking for. However, there's a second, far more tantalizing source of B modes: primordial gravitational waves generated during inflation. Recall that inflation is this hypothetical period of exponential expansion in the very early universe, a cosmic growth spurt that stretched quantum fluctuations to astronomical scales. If inflation is correct, it would have also generated ripples in the fabric of space-time itself, gravitational waves that would have left a unique and specific B-mode polarization signature in the CMB. Detecting these primordial B modes would be a monumental discovery, a smoking gun for inflation, and a direct probe of physics at energies far beyond anything we can achieve in terrestrial laboratories. It would be like finding the missing piece of a cosmic puzzle, a key that unlocks a whole new level of understanding about the universe's origin and evolution. The search for primordial B modes is a major frontier in modern cosmology, a high-stakes quest that has captivated scientists around the world. It is a race against time, a battle against noise, and a testament to our unwavering desire to understand the universe's deepest secrets. What instruments will be brought to bear in this quest? And what obstacles must be overcome to finally detect these elusive signals from the dawn of time? Prepare yourself. The next chapter in this cosmic detective story is just beginning, and the stakes are astronomically high. So, we are in the hunt for gravitational waves. But as these ancient photons travel across billions of light years, what happens when they encounter something truly massive, something with gravity so intense it bends even light itself? Is it a cosmic mirage? A trick of the light? The answer is both simpler and far more profound than you might imagine its gravitational lensing. Consider this. Einstein's theory of general relativity predicts that massive objects warp the fabric of space-time, creating what we experience as gravity. Now imagine a beam of light, a CMB photon on its journey to our telescopes. If that photon passes near a massive object like a galaxy or a cluster of galaxies, its path will be bent, its trajectory altered by the gravitational field. It's like placing a magnifying glass between your eye and an object. The light from the object is bent and distorted as it passes through the lens. In the case of gravitational lensing, the massive object acts as the lens, bending and distorting the light from the CMB. This bending can create multiple images of the same background object, or it can stretch and smear the image into arcs and rings. It's a cosmic hall of mirrors, where reality itself is warped by gravity. But why should we care about these distorted views? Why is gravitational lensing so important to cosmologists? The answer lies in what it tells us about the distribution of matter in the universe. You see, most of the matter in the universe is invisible. It's dark matter, the mysterious substance that makes up about 27% of the cosmos. We can't see dark matter directly, but we can detect its gravitational effects on visible matter and on light. Gravitational lensing allows us to map the distribution of dark matter throughout cosmic history. By measuring how the CMB photons are bent and distorted, we can infer the presence and distribution of the intervening mass, including the dark matter that would otherwise be invisible. It is like shining a light on the unseen, revealing the hidden architecture of the universe. Think of it like this. Imagine you are trying to find a hidden object in a dark room. You can't see the object directly, but you can shine a flashlight on the surrounding walls and see how the light is bent and scattered. By analyzing the patterns of light and shadow, you can infer the shape and location of the hidden object. That is precisely what gravitational lensing allows us to do with dark matter. By analyzing the distortions in the CMB, we can create a map of the dark matter distribution, revealing the scaffolding upon which galaxies and clusters of galaxies are built. It's an ancient map from 380,000 years after the Big Bang, but it's been subtly altered to tell us about everything that happened between then and now. But gravitational lensing is not just about mapping dark matter. It also provides a powerful tool for studying the properties of galaxies and clusters of galaxies. By analyzing the lensed images, we can learn about their mass, their shape, and their internal structure. It's like having a cosmic microscope, allowing us to zoom in on distant objects and study them in unprecedented detail. Consider the analogy of looking at a distant city through a heat haze. The heat haze distorts the image, making it blurry and difficult to see. But by analyzing the patterns of distortion, we can infer the temperature and density of the air. Similarly, by analyzing the distortions in the CMB, we can infer the properties of the intervening galaxies and clusters. The effect is subtle. Gravitational lensing of the CMB causes minute distortions, and it requires the most precise instruments to measure the minute fluctuations in temperature and polarization. But by carefully analyzing these subtle effects, cosmologists are opening a new window into the universe. But that's not all. Gravitational lensing also offers a unique way to probe the inflationary epoch, that period of exponential expansion in the very early universe. As we discussed earlier, inflation is thought to have generated primordial gravitational waves, ripples in the fabric of space-time that would have left a specific B-mode polarization signature in the CMB. Detecting those primordial B-modes is a major goal of modern cosmology, but it's a difficult task because the gravitational lensing can also produce B-modes blurring the signal from inflation. By understanding and carefully removing the effects of gravitational lensing, scientists can more easily find any traces of the signature of gravitational waves from the very earliest epochs of the universe. It is a delicate dance, a subtle interplay between gravity and light that allows us to see the unseen and to understand the universe in all its complexity. The story doesn't end there. The subtle distortions of gravitational lensing hint at an even more bizarre possibility, a fleeting moment in the universe's infancy. But that's not all. Gravitational lensing also offers a unique way to probe the inflationary epoch, that period of exponential expansion in the very early universe. As we discussed earlier, inflation is thought to have generated primordial gravitational waves, ripples in the fabric of space-time that would have left a specific B-mode polarization signature in the CMB. But how did it all begin? Consider the vast emptiness of space and time, a mere fraction of a second after the Big Bang. What if, in that unimaginably short period, the universe underwent a growth spurt of epic proportions? An expansion so rapid, so violent, that it stretched the very fabric of space-time itself. This, in essence, is the theory of cosmic inflation, and it's a mind-bending idea that attempts to explain some of the biggest mysteries surrounding the cosmic microwave background. Imagine taking a small balloon and drawing a few dots on its surface. As you inflate the balloon, the dots get farther and farther apart. Now imagine that balloon expanding not gradually, but exponentially, doubling in size every fraction of a second. That's inflation on a cosmic scale. A period of accelerated expansion that stretched the universe from smaller than a subatomic particle to the size of a grapefruit in a tiny sliver of a second. Some even say it was less than a trillionth of a trillionth of a trillionth of a second. So why is inflation necessary? What problems does it solve? Well, remember that incredible uniformity of the CMB? How could regions of the universe that were never in causal contact have the same temperature? Inflation provides a possible answer. Before inflation, the entire observable universe was contained in a tiny, causally connected region. This region could have reached thermal equilibrium, ensuring that everything was at the same temperature. Then, inflation stretched this tiny region to an enormous size, preserving the uniformity across vast distances. It is like taking a small sample of water, ensuring that it has a uniform temperature, and then spreading it out over an enormous swimming pool. The water in the pool will still have the same temperature, even though it is now spread out over a much larger area. Inflation also explains the origin of those tiny temperature fluctuations, the seeds of galaxies and clusters of galaxies. According to quantum mechanics, even the emptiest space is not truly empty. It is filled with tiny quantum fluctuations, fleeting appearances and disappearances of particles and energy. Inflation stretched these quantum fluctuations to astronomical scales, freezing them into the fabric of space-time. These stretched fluctuations became the density variations that gravity amplified over billions of years to form the cosmic structures we see today. It's like taking a microscopic imperfection and magnifying it to the size of a mountain. If there was no period of inflation, galaxies would never form, and humans would not exist. Consider it this way. Inflation stretched quantum fluctuations to astronomical scales, seeding the structures we see today. These quantum fluctuations could not be explained any other way. Now, is there any direct evidence for inflation? That's where the CMB comes in. The patterns of temperature fluctuations in the CMB are consistent with the predictions of inflation. The size, shape, and distribution of these fluctuations match what we would expect if they were generated by the stretching of quantum fluctuations during an inflationary epoch. But the strongest evidence for inflation would be the detection of primordial gravitational waves. As we discussed earlier, inflation would have generated ripples in the fabric of space-time that would have left a specific B-mode polarization signature in the CMB. Finding those primordial B-modes is the holy grail of inflationary cosmology, and scientists around the world are actively searching for them. The detection of these gravitational waves would be a direct confirmation of inflation and would provide invaluable information about the physics of the very early universe. Inflation is still unproven, but all current evidence points to the theory being accurate. The inflationary theory is widely accepted, but scientists still need more information. As the search for these gravitational waves continues, a nagging question arises. a subtle whisper in the data that refuses to be ignored. What if something isn't quite right? What if there are anomalies, unexpected patterns that challenge our understanding of the early universe? Are our models correct, or is there something else we don't know? But that's not all. Gravitational lensing also offers a unique way to probe the inflationary epoch, that period of exponential expansion in the very early universe. As we discussed earlier, inflation is thought to have generated primordial gravitational waves, ripples in the fabric of space-time that would have left a specific B-mode polarization signature in the CMB. But how did it all begin? As the search for these gravitational waves continues, a nagging question arises, a subtle whisper in the data that refuses to be ignored. What if something isn't quite right? What if there are anomalies, unexpected patterns that challenge our understanding of the early universe? Are our models correct, or is there something else we do not know? What if the universe, in its infancy, pulled one last trick on us, a cosmic sleight of hand that has us chasing shadows? Consider this. Cosmologists are not just looking for any kind of gravitational waves. They are hunting for primordial gravitational waves, the echoes of inflation itself. These are not the gravitational waves produced by colliding black holes or merging neutron stars, events that are relatively common in the universe. Instead, they are looking for something far more ancient, something that originated in the first fraction of a second after the Big Bang. These waves, if found, would be a direct link to inflation itself, proving it occurred. Think of it like listening for a faint melody played on a cosmic harp, a melody so subtle that it is almost drowned out by the noise of the universe. These primordial gravitational waves would have stretched and squeezed space-time in a particular way, creating a unique pattern of polarization in the cosmic microwave background, a swirling pattern known as B-modes. But here's the challenge. B-modes can also be produced by other phenomena such as the gravitational lensing. The subtle bending of light by intervening galaxies can mimic the signal of primordial gravitational waves, making it difficult to distinguish between the two. It is like trying to hear that faint melody while standing next to a construction site. To find the primordial gravitational waves, cosmologists have to carefully subtract out all the other sources of B-mode polarization, a painstaking process that requires incredibly precise measurements and sophisticated data analysis techniques. The instruments used to detect these B-modes include some of the most sensitive ones that mankind has ever created. This is the quest, one of the most exciting challenges in modern cosmology. It is a hunt for the faintest echoes of creation, a search for the missing link in our understanding of the universe. And, should they be found, these subtle signatures in the CMB have the potential to unlock the secrets of inflation, revealing what the universe was like at energies 1 trillion times higher than what can be created in the Large Hadron Collider. Many top scientific minds are currently working on this quest, using advanced telescopes and scientific analysis to help find the gravitational waves. Imagine the moment of discovery. The scientists look at the data and all of a sudden they see an unmistakable swirl, the telltale sign of primordial gravitational waves. It would be a moment of pure elation, a culmination of decades of work. The discovery could possibly lead to a Nobel Prize and rewrite the cosmology textbooks. It could open up a new area of physics and lead to new findings about dark matter and dark energy. This quest has driven countless numbers of engineers to build even more powerful telescopes with even greater sensitivity. To even test these new telescopes, they are placed in some of the harshest environments on Earth, from the high deserts of Chile to the frozen plains of Antarctica. As each new instrument comes online, scientists have a greater chance to detect these primordial gravitational waves and solve some of the greatest mysteries. But even if the instruments are improved and the B-modes are detected, scientists must face an important fact. There are subtle anomalies, the cold spots and unexpected alignments that lurk in the data, teasing at the edges of our understanding. Could these be statistical flukes, random noise in the cosmic symphony? Or could they be something more profound, a hint of new physics or even evidence of universes beyond our own? But even if the instruments are improved and the B modes are detected, scientists must face an important fact. There are subtle anomalies, the cold spots, and unexpected alignments that lurk in the data, teasing at the edges of our understanding. Could these be statistical flukes, random noise in the cosmic symphony? Or could they be something more profound, a hint of new physics or even evidence of universes beyond our own? Consider the maps of the cosmic microwave background. For the most part, they confirm the standard cosmological model. The hot spots and cold spots align with theoretical predictions, providing strong evidence for the Big Bang and inflation. But then you notice something odd, a region of the sky that just doesn't fit. It's too cold, too large, and just plain weird. This is the cosmic cold spot, and it's one of the most intriguing anomalies in the CMB. Imagine staring at a perfectly patterned tapestry, only to find a single glaring imperfection. That's the cold spot. It's a patch of sky that is significantly colder than its surroundings, a dip in temperature that defies easy explanation. This cold spot isn't just a tiny blip. It is a vast expanse, spanning approximately 5 degrees on the sky. To put that in perspective, that's about 20 times the size of the moon as seen from Earth. So what could cause such a massive and unusually cold region? Is it simply a statistical fluke, a random fluctuation in the CMB temperature that just happened to occur by chance? While that's certainly a possibility, the odds of such a large and cold region appearing randomly are incredibly low, prompting scientists to explore more exotic explanations. One possibility is that the cold spot is a sign of new physics, something beyond the standard cosmological model. Could it be evidence of a topological defect, a kind of cosmic string or texture left over from the early universe? These defects are hypothetical objects that could have formed during phase transitions in the early universe, and they could have left their imprint on the CMB. Or could it be evidence of a collision with another universe, a bubble universe that bumped into our own in the distant past? These are very exciting possibilities, but the reality is probably less so. Perhaps the most intriguing explanation involves something called the integrated Sachs-Wolf effect, or the ISW effect. This effect predicts that CMB photons can lose energy as they travel through large voids in the universe, regions where the density of matter is lower than average. Now imagine a vast void, spanning billions of light years, lying between us and the CMB. As the CMB photons travel through this void, they would lose energy, becoming slightly colder. Could the cold spot be the result of the ISW effect caused by such a void? In 2007, scientists discovered a large void in the direction of the cold spot, lending some support to this idea. But even this explanation is not without its challenges. The void doesn't seem to be large enough or empty enough to fully account for the temperature drop in the cold spot. There is something else the scientists have considered. Is the cold spot actually a portal to another universe? A door into another dimension? Highly unlikely, but that doesn't stop scientists from looking into the math of the science. But this remains just one possible theory of many. The cold spot remains a puzzle, a cosmic mystery that continues to challenge our understanding of the universe. But as new data pours in from ground-based telescopes, and new space-based telescopes are planned, scientists believe they will eventually unlock the secrets of this anomaly. As with all the mysteries of the universe, we simply need better and more powerful telescopes, and so the quest continues, and maybe, just maybe, we'll discover if there are other universes. And while the cold spot remains one of the biggest anomalies that cosmologists are currently studying, there are, lurking out on the edges of perception, other puzzles that continue to challenge and baffle astronomers. And while the cold spot remains one of the biggest anomalies that cosmologists are currently studying, there are, lurking out on the edges of perception, Other puzzles that continue to challenge and baffle astronomers. Imagine meticulously crafting a map detailing every hill, every valley, every contour with painstaking precision. Then you notice something odd. Certain landmarks seem to line up in a way that's statistically improbable, as if an unseen hand had nudged them into alignment. This is, in essence, what cosmologists have encountered when studying the largest scale features of the cosmic microwave background. They've found subtle, yet persistent alignments that defy easy explanation, and have even earned a rather ominous nickname, the axis of evil. Now, why axis of evil, you might ask? Well, it's not meant to imply anything malevolent or sinister, no cosmic forces of darkness at play. The name simply reflects the unexpected and somewhat unsettling nature of these alignments, a challenge to our fundamental assumptions about the universe. Several research teams have reported that the CMB's quadrupole and octupole moments, that is the largest scale temperature fluctuations, tend to align with each other and with the plane of the solar system. What is the significance of this alignment? After all, wouldn't it make sense that most of the major structures in the universe would align on a single axis? The standard cosmological model predicts that the CMB should be statistically isotropic, meaning that its properties should be the same in all directions. These alignments, however, suggest that there might be a preferred direction in the universe, a violation of this fundamental principle. It is as if you spun a ball, and instead of having the markings on the ball spread out randomly, they all align on a single line. Is this a problem with our instruments? That is what many scientists wondered. This is what the cosmologists wondered. A group of scientists wanted to make sure it wasn't instrument error. They scrutinized the data to make sure that their instruments were not flawed. They went back over their own data to see if they could find any kind of flaw in their findings. But the more and more they worked, they found that they couldn't make it go away. The more they worked, the more obvious it became that this was a part of the sky. Could these alignments be caused by some unknown foreground contamination, something that is skewing our measurements of the CMB? Perhaps it is caused by some unknown factor that we simply don't have the instruments to detect. Cosmologists have carefully analyzed the data to remove any potential foregrounds, but the alignments persist. The data is accurate, or they are not quite sure what it is. Perhaps the biggest question that most scientists have is, does this show that the Earth is somehow special? Are we at some kind of important place in the universe? Could the fact that the Earth is at some unique and important place in the universe cause errors? Does it cause things to be warped and moved around when we look at it? It might be easy to look past these concerns since there are so many other amazing discoveries in science that seem to add up. But the scientists keep asking themselves if these problems could lead to bigger problems. But perhaps the most intriguing explanation is that these alignments are a sign of something truly new, something that lies beyond the standard cosmological model. Could they be a hint of a more complex topology of the universe, or even evidence of extra dimensions beyond the 3 spatial dimensions we experience? These are mind-bending possibilities that would require a fundamental rethinking of our understanding of the cosmos. Imagine if these alignments can change not just astronomy textbooks, but the very nature of science itself. Consider another anomaly, a subtle difference between the hemispheres of the CMB. Some studies have suggested that there might be a slight asymmetry in the temperature fluctuations between the northern and southern hemispheres of the sky. One hemisphere might be slightly hotter or have slightly larger temperature fluctuations than the other. This, too, is unexpected and challenges the assumption of statistical isotropy. Could these hemispherical asymmetries be related to the axis of evil, perhaps caused by the same underlying phenomenon? Or could they be a separate puzzle, a different piece of the cosmic puzzle that we are still trying to solve? The significance of these anomalies is still debated, but they serve as a reminder that our understanding of the universe is far from complete. There may be surprises lurking in the data, subtle clues that could lead to new discoveries and a deeper understanding of the cosmos. Perhaps these anomalies are like the faint whispers of a cosmic conspiracy, hinting at a hidden order that we have yet to uncover. What seems to be the most puzzling is these puzzles continue to persist today. They may be the key to solving the riddles of the cosmos or a cruel joke that reality is playing on all of us. Could these inconsistencies lead to a new standard of measurement? Maybe all these anomalies will lead to a new direction in science. Or maybe they are just tricks of the light. It's as if the universe is whispering to us, but we haven't completely learned its language. But even if the instruments are improved and the B modes are detected, scientists must face an important fact. There are subtle anomalies, the cold spots and unexpected alignments that lurk in the data, teasing at the edges of our understanding. Could these be statistical flukes, random noise in the cosmic symphony? Or could they be something more profound, a hint of new physics, or even evidence of universes beyond our own? But what if, instead of looking outwards across the vastness of space and time, we turn our gaze closer to home? What if the universe itself is playing a trick on us, not with faint whispers from the early cosmos, but with discrepancies in our measurements of its current expansion rate? Could it be that what we thought was a well-understood fundamental constant is actually a source of profound confusion, potentially unraveling our entire cosmological framework? Imagine attempting to build a bridge, only to discover that the measuring tape you've been using is slightly off. The entire structure, carefully designed and meticulously constructed, could be compromised. This, in essence, is the challenge facing cosmologists today with the Hubble tension. The Hubble constant, named after the pioneering astronomer Edwin Hubble, is a fundamental parameter that describes the rate at which the universe is expanding. It tells us how fast galaxies are moving away from us due to the expansion of space itself. Now, you might think that measuring this constant would be a straightforward task. After all, we have incredibly powerful telescopes and sophisticated techniques at our disposal. But surprisingly, the Hubble constant is proving to be remarkably difficult to pin down. There are two primary ways to measure the Hubble constant. The first method relies on observations of the cosmic microwave background, that ancient light from the early universe. By studying the patterns of temperature fluctuations in the CMB, cosmologists can infer the value of the Hubble constant with incredible precision. These measurements are based on our understanding of the physics of the early universe and the standard cosmological model. The second method uses what we might call the cosmic distance ladder. This involves measuring the distances to nearby objects, such as Cepheid variable stars and Type 1a supernovae, and then using these measurements to calibrate distances to more distant objects. Type 1a supernovae are what scientists call standard candles. These distant objects act as markers across the universe, allowing scientists to measure their distance with a good deal of accuracy. This method is based on observations of the local universe and is independent of any cosmological model. So what's the problem? The measurements of the Hubble constant derived from the CMB and from the local universe disagree. The CMB measurements suggest a value of around 67 kilometers per second per megaparsec, while the local measurements suggest a value of around 73 kilometers per second per megaparsec. That's a difference of about 9%, which might not sound like much. But in cosmology, where precision is paramount, this discrepancy is highly significant. This is known as the Hubble tension, and it represents a potential crack in the standard cosmological model. If the two measurements are correct, then something is fundamentally wrong with our understanding of the universe. What could be causing this tension? Are there unaccounted for systematic errors in our measurements? Or does the discrepancy point to new physics beyond the standard lambda CDM model? One possibility is that there is some unknown systematic error in one or both of the measurements. Perhaps we are misinterpreting the CMB data, or perhaps our distance measurements to supernovae are not as accurate as we thought. Cosmologists are working hard to scrutinize every aspect of these measurements to identify any potential sources of error. It's like trying to find a needle in a cosmic haystack, a subtle flaw that could be throwing off our entire understanding of the universe. Another possibility is that the Hubble tension is a sign of new physics, something beyond the standard lambda CDM model. Perhaps there is some new form of dark energy that is affecting the expansion rate of the universe, or perhaps there is some new type of particle that is interacting with the CMB. These are exciting possibilities that could revolutionize our understanding of the cosmos. What if there's more to the universe than we could possibly understand? Some scientists have even proposed more exotic explanations for the Hubble tension, such as the existence of a multiverse, where our universe is just one of many bubbles in a vast cosmic foam. In this scenario, the Hubble constant could be different in different universes, and our measurements might be skewed by the influence of neighboring universes. Are we sure of all the factors that could affect the expansion of the universe? Could there be new data and new science out there that we don't even know about? The Hubble tension is one of the biggest mysteries in cosmology today, and it is driving a flurry of research activity. Scientists are using new telescopes and new techniques to make more precise measurements of the Hubble constant, hoping to resolve the discrepancy and shed light on the underlying cause. The next generation of cosmic explorers is on the horizon. But what will they find? Will they help solve this cosmic riddle, or will it just create more confusion? The data could be right around the corner. But even if the instruments are improved and the B modes are detected, scientists must face an important fact. There are subtle anomalies, the cold spots and unexpected alignments that lurk in the data, teasing at the edges of our understanding. Could these be statistical flukes, random noise in the cosmic symphony? Or could they be something more profound, a hint of new physics or even evidence of universes beyond our own? If the Hubble constant puzzle leaves us grappling with the expansion rate, perhaps even more ghostly players from the early universe influenced how that ancient light was patterned. What if the very fabric of the CMB, that photograph of the baby universe, holds clues to the masses of particles so elusive they're often called ghost particles? We're talking about neutrinos. These subatomic particles are among the most abundant in the cosmos. Trillions of them stream through our bodies every second, unfelt and unnoticed. They're created in nuclear reactions inside stars, in supernovae explosions, and even in the Big Bang itself. Neutrinos interact so weakly with matter that they can pass through the entire Earth with only a tiny chance of colliding with anything. It is as if they have no substance. But here's the thing. Despite their elusiveness, neutrinos have mass. Not a lot, mind you, but some. The question is how much? Figuring this out is one of the great challenges in particle physics, and surprisingly, the cosmic microwave background can help. How can the CMB possibly give us the weight of a particle that barely interacts with anything? It all boils down to their influence on the early universe. In the first few moments after the Big Bang, the universe was filled with a seething soup of particles, including vast numbers of neutrinos. These neutrinos, even with their tiny masses, exerted a gravitational pull. This affected the expansion rate of the universe and the formation of the very first structures. It is like adding a teaspoon of salt to a large bowl of soup. It might seem insignificant, but it changes the entire flavor of the meal. Think of the CMB as a snapshot of this early cosmic dance. The patterns of hot and cold spots, those subtle temperature fluctuations, were influenced by the presence and behavior of neutrinos. The more massive the neutrinos, the more they would have suppressed the growth of small-scale structures, leaving a distinct imprint on the CMB. This imprint is subtle, mind you, but detectable with the right instruments and analysis. It's like looking at footprints in the sand. The size and shape of the footprints can tell you something about the size and weight of the person who made them. It requires careful measurements and statistical analysis, but in the end, you can estimate a person's height and weight. Scientists can use statistical means to figure the size and weight as well. By precisely measuring the CMB patterns, cosmologists can constrain the total mass of all three types of neutrinos. This provides a unique cosmological probe of particle physics properties. The CMB acts as a sort of cosmic scale, weighing these ghost particles by their gravitational influence on the early universe. It's a clever trick, using the largest structure we know, the cosmos, to weigh the smallest known particles. The CMB is an incredibly old tool that is used to measure incredibly small things. What makes this so exciting is that it provides an independent way to measure neutrino masses, complementing the efforts of particle physics experiments here on Earth. Experiments at places like the Super Kamiokande detector in Japan are directly searching for neutrino mass by studying how neutrinos change from one type to another. The CMB provides a completely different approach, a cosmic consistency check that can help to confirm or refute the results of these terrestrial experiments. And it can tell us things about the neutrinos that Earth-based experiments just cannot do. The CMB allows scientists to infer data from how the universe acted 13.8 billion years ago. It gives unique insight into how the cosmos was shaped. It adds data that all scientists from all areas of scientific study can use to get a better view of the universe. Consider the words of Enrico Fermi, the famed physicist who made groundbreaking contributions to nuclear physics. He once said, "There are two possible outcomes. If the result confirms the hypothesis, then you've made a measurement. If the result is contrary to the hypothesis, then you've made a discovery." This perfectly encapsulates the spirit of the CMB neutrino mass measurements. Whether they confirm our existing understanding or reveal something new and unexpected, we are guaranteed to learn something profound about the nature of these elusive particles and the universe they inhabit. But what happens when we try to combine all of these different lines of evidence, from the CMB to supernovae to these ethereal neutrinos? Do all the pieces fit together into a coherent picture? Or are there lingering tensions, subtle disagreements that hint at deeper mysteries? The universe is filled with subtle clues that we just need to learn how to understand. And are all the telescopes that we send into space the only way we are going to find these answers? What if, by bringing these telescopes back to the ground, we could better understand the universe that we live in? We need a clearer picture. But what happens when we try to combine all of these different lines of evidence, from the CMB to supernovae to these ethereal neutrinos? Do all the pieces fit together into a coherent picture? Or are there lingering tensions, subtle disagreements that hint at deeper mysteries? The universe is filled with subtle clues that we just need to learn how to understand. And are all the telescopes that we send into space the only way we are going to find these answers? What if, by bringing these telescopes back to the ground, we could better understand the universe that we live in? We need a clearer picture. What if the next giant leap in CMB research doesn't involve escaping Earth's atmosphere, but mastering it? After all, for centuries, some of humanity's greatest discoveries have been made from terra firma. Instead of solely relying on space missions, the next stage involves massive ground-based observatories strategically placed to peer through the clearest windows on our planet. Picture this: a high-altitude desert in Chile, the Atacama Desert, one of the driest places on Earth. The air is thin, the sky is dark, and the atmosphere is incredibly stable, making it an ideal location for observing the cosmos. It is here, nestled among the towering peaks of the Andes, that you find the Atacama Cosmology Telescope, or ACT. The telescope is perched atop a mountain called Cerro Toco. The location offers an atmosphere that is perfect for high-frequency observation of the cosmic microwave background radiation, or travel to the opposite end of the Earth, to the frozen continent of Antarctica, where the South Pole Telescope, or SPT, stands sentinel against the perpetual darkness. The extreme cold, the high altitude, and the absence of atmospheric moisture make the South Pole a remarkably transparent window to the universe. The South Pole Telescope is 1.3 kilometers away from the Amundsen-Scott South Pole Station. This location provides a unique, stable environment for CMB observation. These aren't your grandfather's telescopes. They are sophisticated instruments designed to make detailed measurements of the cosmic microwave background with incredible precision. These observatories have been designed to observe millimeter-wave light. This is where the oldest light in the universe can be found. But why build telescopes on the ground when space-based missions offer a clearer view? Ground-based telescopes can make observations for far longer periods than space-based observatories. This means they can map the cosmic background on smaller scales. These two different vantage points both have advantages and disadvantages that have to be weighed for the best possible outcome. The answer lies in a combination of factors. First, ground-based telescopes are much cheaper to build and operate than space-based missions. Launching a satellite into orbit can cost hundreds of millions, even billions of dollars, while building a telescope on the ground is relatively inexpensive. Think of it as comparing the cost of building a house to the cost of launching a rocket. Second, ground-based telescopes can be easily upgraded and maintained. New instruments can be added, and existing ones can be repaired without having to launch another mission into space. It is a more hands-on, iterative approach. While they do have to contend with atmospheric conditions, the cost-effectiveness and long-term usability of ground-based telescopes can easily offset the difficulties. Atmospheric conditions can vary with the changes of the seasons, which means the data collection has to also be altered depending on whether the weather is good or bad. These ground-based observatories are not replacements for space missions. They are complementary tools, each with its own strengths and weaknesses. Space missions provide a broad, all-sky view of the CMB, while ground-based telescopes can focus on smaller patches of the sky with higher resolution and sensitivity. They aim for deeper, higher-resolution maps of smaller sky patches, focusing on polarization and lensing, which space-based missions sometimes have difficulty obtaining. They are crucial for hunting B modes. Hunting them requires extremely sensitive detectors and pristine skies that are far from urban light. Imagine it like this. Space missions paint the broad strokes of a masterpiece, while ground-based telescopes add the fine details, the subtle shading, and the intricate textures. Beyond the Atacama Cosmology Telescope and the South Pole Telescope, a new generation of ground-based observatories is on the horizon. Projects like the Simons Observatory and CMB-S4 represent the next leap forward in CMB research. The Simons Observatory, for example, will consist of a suite of new telescopes located in the Atacama Desert designed to map the CMB with unprecedented sensitivity. This experiment has 5 goals that it hopes to address. The first is that the universe began with rapid inflation. The second is to catalog all the matter in the universe. The third is that scientists hope to understand the role of neutrinos in the evolution of the universe. The fourth is to find light-dark matter, and the fifth is to understand strange signals found in previous studies. CMB-S4 is an even more ambitious project, a next-generation experiment that will combine observations from both the Atacama Desert and the South Pole, creating the most powerful CMB observatory ever built. With its increased sensitivity and sky coverage, CMB-S4 will be able to probe the inflationary epoch with greater precision than ever before, searching for those elusive primordial gravitational waves and testing our fundamental understanding of the universe. One of the more difficult aspects of the project is finding scientists and engineers who are willing to work in such harsh environments. The scientists and engineers that keep all of these projects running are hardworking, and they enjoy their work. The data that they collect is incredibly important. The data can tell all scientists new information about the early universe. These ground-based observatories are crucial for hunting B modes and refining parameters. What secrets will they reveal? What new insights will they provide into the origin and evolution of the cosmos? They may find information about things that scientists have been looking for dozens and dozens of years. The next era in cosmic exploration won't just rely on what we can see from above, but the next chapter will be written using those telescopes that remain firmly planted on the ground. But the ground isn't the only vantage point. In the relentless pursuit of cosmic understanding, where else might we look for answers, and where else might we try to place the next powerful telescope? The next era in cosmic exploration won't just rely on what we can see from above, but the next chapter will be written using those telescopes that remain firmly planted on the ground. but the ground isn't the only vantage point. In the relentless pursuit of cosmic understanding, where else might we look for answers, and where else might we try to place the next powerful telescope? What if the key to unlocking the universe's deepest secrets lies not just in refining existing instruments, but in launching a new generation of space missions specifically designed to complement ground-based efforts and push the frontiers of cosmology even further? Think about it. Ground-based telescopes, as powerful as they are, can only observe the universe through the narrow windows of Earth's atmosphere. They are limited by weather conditions, atmospheric turbulence, and the constant glow of city lights. Space-based missions, on the other hand, offer a pristine, unobstructed view of the cosmos, free from these terrestrial limitations. They can observe the entire sky day and night and can detect wavelengths of light that are absorbed by the atmosphere. Future space missions are also planned to complement ground-based efforts, potentially offering all sky coverage optimized for B-mode detection. What if instead of looking at a fraction of the sky, you could look at all of it? That is what the next generation of space missions is setting out to do. These missions are designed to detect those elusive B-mode polarization patterns, the faint signatures of primordial gravitational waves from the inflationary epoch. They will be able to measure all of the cosmic background. Japan's LIGHTBIRD mission is specifically designed to search for the faint signature of primordial gravitational waves. Think about the name for a moment. LIGHTBIRD. It evokes images of something delicate, something light, soaring through the cosmos in search of hidden truths. This mission is the culmination of international collaboration, bringing together scientists and engineers from around the world to tackle one of the biggest challenges in cosmology. Why Japan, you may ask? Japan has a long history of innovation and excellence in space exploration and astrophysics. Japanese scientists have been at the forefront of CMB research for decades and have developed some of the most advanced technologies for detecting faint microwave signals. Japan has invested in the science of light and the science of finding dark matter to find the information that no one else has been able to gather. What makes LIGHTBIRD so special? It is specifically designed to target the B-mode polarization signal with unprecedented sensitivity and accuracy. It will survey the entire sky over a period of 3 years, mapping the CMB polarization patterns with exquisite detail. LIGHTBIRD has several unique features. It has a large array of highly sensitive detectors, capable of measuring tiny variations in the polarization of light. It has a sophisticated system for removing foreground contamination such as emission from our own galaxy. Also, it will orbit the Sun in sync with Earth. These future endeavors promise to push the frontiers of cosmology even further. But what if there's something we haven't even considered? These new missions will provide an even clearer picture of the universe and help determine some of the parameters to which scientists have been searching. Imagine what this information could do. By refining existing measurements and discovering previously unknown properties and forces, scientists can come closer than ever to constructing a complete model. But what will happen if we discover new things that make us reevaluate our current theories? This is something that is going to have to be considered as new missions are launched into space. It can be difficult to change previous thoughts when there is so much evidence. What new secrets will they unlock? Will they finally detect those elusive primordial gravitational waves, providing definitive evidence for inflation and opening a window into the very first moments of the universe? Will they shed light on the nature of dark matter and dark energy, those mysterious components that make up the vast majority of the cosmos? Will they reveal new anomalies in the CMB, challenging our understanding of the universe and pointing towards new physics? These future endeavors promise to push the frontiers of cosmology even further, and it's not just LIGHTBIRD. Other space missions are in the planning stages, each designed with unique capabilities and objectives. Some will focus on mapping the CMB polarization with even greater precision, while others will search for new types of particles or probe the large-scale structure of the universe. Future endeavors and collaborations with other countries will also help further the knowledge of the cosmos. These new missions will require new innovations. As human beings explore farther and farther out into space, it is up to those people here to provide the information and technology that will be needed to survive. Future innovations will include new and improved detectors as well as materials to better handle the hazards of space. These future endeavors are more than just scientific experiments. They are voyages of discovery, driven by our innate curiosity and our unwavering desire to understand the universe in which we live. They represent the next chapter in the story of the cosmic microwave background, a story that has captivated scientists and the public alike for more than half a century. The answers may surprise you. Perhaps it's time to consider the bigger picture. Beyond the individual discoveries, beyond the specific parameters measured, what does it all mean? We've been on a journey, a quest to understand the cosmic microwave background, this echo of creation that resonates across 13.8 billion years. What began as static on an antenna has evolved into one of the most powerful tools in cosmology, a direct image of our cosmos in its infancy. This isn't just about confirming a theory, it's about understanding where we all come from. The CMB, this snapshot of the baby universe, confirms the Big Bang, no small feat. But it doesn't just confirm, it details. It meticulously paints a picture of the universe's composition, its history, and its evolution. It's a cosmic family album, revealing our ancestors in their earliest forms. Think about the sheer audacity of it. We, creatures who have only been around for a blink of an eye in cosmic terms, are using our intellect and ingenuity to unravel the secrets of the universe. We are deciphering a message that has been traveling for billions of years, a message that was written in the language of light and gravity. It is as if we are archaeologists, carefully excavating the ruins of the early universe, piecing together the fragments of its past. And perhaps most remarkably, the CMB provides stringent tests of fundamental physics, like inflation. These tests aren't merely academic exercises. They are essential for understanding the laws that govern the universe, the forces that shape our reality. We're talking about pushing the boundaries of human knowledge, venturing into the unknown with courage and determination. It would not be overstating the situation to say that the cosmic microwave background represents the ultimate photograph, showing a direct connection to our cosmic origins. It is as if the entire cosmos is a movie and the cosmic microwave background is the opening scene. It is a profound connection to our cosmic origins, revealing our place within the grand cosmological narrative. It is a story that begins with a Big Bang and continues to unfold even today. Consider this. You are not just a passive observer in this cosmic drama. You are an active participant. You are made of star stuff, forged in the hearts of dying stars billions of years ago. The atoms in your body were once part of the cosmic plasma that gave rise to the CMB. You are, in a very real sense, a child of the universe connected to it in ways that are both profound and mysterious. Every breath you take contains atoms that were created in the Big Bang. The story of the cosmic microwave background is not just a story about the universe, it is a story about us. It is a story about our quest for knowledge, our relentless pursuit of understanding, and our unwavering belief that the universe is knowable. What might have the universe looked like before the bang? Think of the generations of scientists who have dedicated their lives to studying the CMB, from the accidental discovery by Penzias and Wilson to the groundbreaking measurements by COBE, WMAP, and Planck. They are pioneers, explorers, and detectives, all driven by a shared desire to unravel the secrets of the cosmos. They all want to know how everything began. It's a story of human triumph, a testament to our capacity for curiosity and innovation. The story that you have heard in these chapters is a tiny fraction of what has been discovered, and there is so much more to discover. The human mind is very powerful, and there are no limitations to what we can find. What wonders await discovery as we peer ever deeper into the cosmos?